Good morning, friends. I am Meenakshi from BSc Chemistry Honors second year. Today I am going to read a chapter named Thermodynamics 2. So let's start with the introduction, need for the second law, and different statements of the law. The first law of thermodynamics has certain serious limitations. To overcome these limitations, a strong need was there felt to introduce another law called second law of thermodynamics. In a few limitations of a first law and a consequence, some definitions given to second law are briefly given below. A major limitation of first law of thermodynamics is that it merely indicates that in any process there is an exact equivalence between the various forms of energy involved, but it provides no information concerning the feasibility of the process. Yes, that is, whether the process is feasible or not. For example, the first law does not indicate whether heat can flow from cold end to hot end or not. All that it tell is the that if this process occurred, the heat energy gained by one end would be exactly equal to the loss by other end. Similarly, the first law does not tell whether a gas can diffuse from low pressure to high or water can itself run uphill, etc. The second law supplies answer to the above question by stating that all the spontaneous processes like the flow of heat from hot end to cold end, diffusion of gas from high pressure to low pressure, or the flow of water down a hill, etc., are thermodynamically irreversible. First definition. The term spontaneous process used in the above definition means a process which can take without the help of any external agency. The natural process, some of which are mentioned in the definition above, are spontaneous process. However, it may be mentioned here that in term spontaneous does not give an idea about the rate of process, whether the process takes place fastly or slowly. All that it implies is that a process can occur without the help of any external agency. The first law states that when heat is converted into work or the work obtained is equivalent to the heat absorbed, however, it has been seen from the experience that heat absorbed cannot be completely converted into work without leaving some changes in the system or the surroundings. For example, the heat produced in a locomotive is not fully utilized in running a train. A part of it is lost to the surrounding or wasted in overcoming the friction. Hence, the second law is also stated above as the complete conversion of heat into work is impossible without leaving some effects elsewhere. This is the second definition. Besides the above definition, a number of other definitions have also been given to the second law of thermodynamics. Two important ones are: it is impossible to construct a machine functioning in a cycles which can convert the heat completely into equivalent amount of work without producing some changes elsewhere. Without the use of an external agency, heat cannot by itself pass from colder to hotter body. The term functioning in cycle is introduced in the above definition to indicate that the machine must return to a original state. Indicates that the machine must return to its original state at regular intervals so that it can function continuously. Further, it may be recalled that in an isothermal reversible expansion of an ideal gas, del U is 0 so that Q is equals to W. That is, the work done is exactly equal to heat absorbed by the system. In other words, in this process the heat is completely converted into work. However, it is important to observe that this conversion is accompanied by increase in volume of the gas so that the system has undergone a change. A number of other definitions have also been given to the second law of thermodynamics, which we will come across in the succeeding sections of this chapter. The fraction of heat absorbed by a machine that it can transform into work is called efficiency of the machine. Thus, if Q is the heat absorbed and W is the work done, then the efficiency of the machine is given by neta is equals to W upon Q. Neta is a symbol of efficiency. The machine used for conversion of heat into work is called heat engine. In order to bring about this conversion, the engine absorbs heat from heat reservoir at a higher temperature called source and converts a part into work and return the remainder to heat reservoir at lower temperature called the sink. Carnot cycle and its efficiency. In order to calculate the efficiency of a heat engine, Sadi Carnot in 1824 devised a technique called Carnot cycle, a cycle in a process in which a system returns to its original state after a number of successive changes. A process conducted in this manner is called cyclic process. The engine chosen by Carnot, called Carnot engine, for purpose of calculation of efficiency was hypothetical one and cannot be achieved in actual practice. It was selected because it could be subjected to simple thermodynamic treatment. It consists of a cylinder containing 1 mole of an ideal gas as the working substance and fitted with weightless, frictionless piston so that all the operations in the cycles are carried out reversibly. For this reason, it is also called reversible heat engine. The cylinder is supposed to be insulated on all sides except at bottom so that heat can flow to or from system only through the bottom. Further, it is supposed that there are two heat reservoirs, one at high temperature T2 called source and other at low temperature T1 called sink. If some operation is carried out by placing the cylinder in the source or the sink, it can exchange heat within it. Hence, the temperature remains constant so that the process is isothermal. On the other hand, if during operation a cylinder is placed on an insulating material, no heat exchange can take place between the system and the surrounding. Hence, the process is adiabatic. The Carnot cycle consists of four different operations which can be represented on a pressure volume diagram. These operations are carried out as shown in figure. Isothermal expansion. The cylinder containing 1 mole of an ideal gas occupying a volume V1 is placed in contact with source. The gas absorbs heat Q2 from the source and expands isothermally and reversibly till its volume has increased to V2. The path of the process is represented by isothermal curve AB. Since the gas is ideal, the work W1 by 1 mole of the ideal gas will be given by minus W1 is equals to RT2 ln V2 upon V1. Further, for an ideal gas, the work done is equals to heat absorbed Q2 so that minus W1 is equals to Q2 is equals to RT2 ln V2 upon V1. Here, W1 has taken negative and Q2 is positive by latest sign conventions. Adiabatic expansion. The cylinder is now removed from the source and placed in perfectly insulated material so that the gas now expands adiabatically and reversibly. Work is done in the expansion, but since no heat enters or leaves the system, the temperature must fall. And the reversible adiabatic expansion is continued till the temperature has fallen to T1, which is the temperature of the sink. Suppose corresponding volume becomes V3, the path is shown by the adiabatic curve BC. The work done W2 will given by minus W2 is equals to CV bracket T1 minus T2 is equals to minus CV T2 minus T1, where CV is the heat capacity of an ideal gas. Here again WT is negative by the usual sign conventions. Isothermal compression. The cylinder is now removed from the insulating material and placed in contact with sink. The gas is compressed isothermally and reversibly till the volume decreases from V3 to V4. The process is represented by path CD. The work done is taken as positive by usual convention of sign and hence will be given by W3 is equals to RT1 up ln V4 upon V3. During the operation, an amount of heat Q1 exactly equal to W3 will be returned to the sink at T1, that is, heat has been given out by the system using the appropriate convention of sign. Q1 will be negative and W3 will be positive so that minus Q1 is equals to W3 is equals to RT1 ln V4 upon V3. Adiabatic compression. The cylinder is now removed from the sink and the placed against on the insulating material. The gas is then compressed adiabatically and reversibly along dA till the initial state A has regained. The temperature of the gas rises from T1 to T2. The work done is positive by the convention of sign and will be given by W4 is equals to CV T2 minus T1. As the result of these four operations, the system has returned to the original state so that the reversible cycle has been completed. The net work W by the system will be given by W is equals to minus W1 plus minus W2 plus W3 plus W4. And as I have already tell you about what is the value of W1, W2 and W3 respectively. So finally we will get the relation W total work done is equals to RT2 ln V2 upon V1 plus RT1 ln V4 upon V3. Since V1 and V4 lie on one adiabatic curve and V2 and V3 lie on another, it follows that V4 upon V1 gamma raised to the power gamma minus 1 is equals to T2 minus 1. V3 upon V2 whole raised to the power gamma minus 1 is equals to T2 minus T1. Hence, comparing these two equations, we can say that V4 upon V1 whole raised to the power the gamma minus 1 is equals to V3 upon V2 whole raised to the power gamma minus 1. From here, this can be concluded that V4 upon V3 is equals to V1 upon V2. Putting this value in the equation 8, we can say R T2 minus T1 ln V2 upon V1. Dividing the equation 12 by equation 2, we can get W upon Q2 is equals to T2 minus T1 upon T2, which gives the efficiency of Carnot cycle or engine. Carnot isotherm. From equation 13, it is clear that the efficiency of a reversible heat engine depends upon the temperature of source and the sink and is independent of the nature of working substance. Another important observation to be made from the above derivation is that the work done in the cycle is only the one involved in the isothermal operation because the work done in the adiabatic operations cancels one another. Further, as discussed earlier, the work done in the reversible isothermal expansion from A to B is maximum, whereas the work done on the gas during the reversible isothermal compression from C to D is minimum. Hence, the total work done by the system is maximum for the specified condition and therefore the max efficiency is maximum. The result of that follows the Carnot cycle is called Carnot isotherm. The efficiency of a reversible heat engine depends upon the temperature of a source and a sink and is independent of the nature of working substance. In other words, all the reversible heat engines working between same two temperature have the same efficiency. Further, it states that the efficiency of a reversible heat engine is maximum for the given temperature. Since the quantity T2 minus T1 upon T2 is always less than unity, the efficiency of a heat engine is thus always less than unity. In view of the above discussion, the second law of thermodynamics is sometimes defined as follows. The heat engine absorbs a certain amount of heat from the source and converts a part of it into work and return the rest to the sink. In other words, it is impossible to convert the heat completely into work. From the combination of equation 2, 5 and 8, we can say W is equals to Q2 minus Q1 and the net work done of the system is equals to net heat absorbed by the system. Putting the value of W in equation 13, we can get Q2 minus Q1 upon Q2 is equals to T2 minus T1 upon T2. Hence, the efficiency of a heat engine may be given by any one of the following expression. Neta is equals to W upon Q2 is equals to Q2 minus Q1 upon Q2 is equals to T2 minus T1 upon T2. This result derived from the reversible Carnot cycle led to the introduction of a new thermodynamic term called entropy and discussed in the next section. Thermodynamic scale of temperature. From an earlier studies, we are familiar that a thermometer is constructed most commonly by taking suitable amount of mercury in a glass bulb at the end of a capillary tube marking 0 when it is placed in contact with ice and marking 100 when it is placed in boiling water. The length between 2 points is divided into 100 equal particle degrees. The scale of temperature thus obtained is called Celsius scale of temperature. However, because different liquids expand to different extent, their coefficients of expansion are different and also they do not expand uniformly over a given range. Thermometers constructed by using different liquids will show different numerical value of temperature between their fixed point. For example, the body may show the temperature of 28.7 degrees Celsius with the mercury thermometer, but it shows 28.8 degrees Celsius with an alcohol thermometer. The problem was solved by the study of property of gases. It was found that an ideal gas or a perfect gas ceases to exist at a temperature of minus 273.1.73.15 degrees Celsius. This temperature was called 0 degree absolute, and the scale developed on this basis was called perfect gas temperature scale and is found to be independent of the ideal gas taken. However, based on the efficiency of a reversible heat engine, Lord Kelvin was the first to develop a scale of temperature that was independent of the nature of a gas taken in the heat engine. This scale of temperature was called thermodynamic scale of temperature, the Kelvin scale of the temperature. It was found to be identical with the ideal gas temperature scale. The basis of the development of this scale is briefly discussed below. Suppose there are two constant temperature heat reservoirs, one acting as a source and other as a sink, and reversible heat engine operate between them. The temperature of each reservoir on the new scale may be taken as proportional to the quantity of heat absorbed from the source and heat lost to the sink. If Q2 is the heat transfer from the source and Q1 is the heat transfer in the sink, then if their temperature on the thermodynamic or Kelvin scale are represented by theta 2 and theta 1 respectively, then we shall have Q2 upon Q1 is equals to theta 2 upon theta 1. Thus, the ratio of true temperature has been defined as a manner of independent independent of the nature of the thermodynamic substance. Taking the reciprocal on the both sides, we can sides of equation 1 and subtracting the result from unity, 1 minus q1 upon q2 is equals to 1 minus theta 1 upon theta 2. q2 minus q1 upon q2 is equals to theta 2 minus theta 1 upon theta 2. Putting theta 1 0, we can the 0 of the new scale we get q2 minus q1 upon q2 is equals to. This implies that a 0 on the Kelvin scale is the temperature of the sink for reversible heat engine whose efficiency is unity, which is capable of converting heat completely into work. But from equation 14, it may be seen that it is possible only at absolute 0 on ideal gas scale of temperature. This leads to a conclusion that Kelvin scale and gas scale are identical provided the gas is ideal, and the temperature on the thermodynamic scale are therefore expressed in terms of degree Kelvin. Further, it has been found that if the lower fixed temperature is taken as equals to a triple point of water, the Kelvin is exactly equal to Celsius degree. For this reason, the temperature on the absolute scale in which melting point of ice is taken 27.273.16 degrees is often referred as a degree Kelvin. It may be concluded that thermodynamic scale of temperature as defined on the basis of second law of thermodynamics is more basic than that based on the ideal gas because any fluid can be used. However, the ideal gas scale is more practical for laboratory use. Concept of entropy. Entropy as a state function. For a reversible Carnot cycle working between temperature T2 and T1, it has been seen Q2 minus Q1 upon Q2, T2 minus T1 upon T2, where Q2 is the heat absorbed isothermally and reversibly at temperature T2 and Q1 is the heat lost isothermally and reversibly at temperature T1. The above equation may be simplified as 1 minus Q1 upon Q2 is equals to 1 minus T1 upon T2, or Q2 upon T2 is equals to Q1 upon T1, Q upon T is equals to constant. Thus, we conclude that the heat absorbed or lost isothermally and reversibly divided by the absolute temperature at which heat is absorbed or lost is constant quantity for a particular system. Further, in equation 2, Q2 is the heat absorbed at temperature T2 and Q1 is the heat lost at temperature T1. If Q1 is the heat absorbed at temperature T1, equation 2 would be given as Q2 upon T2 is equals to minus Q1 upon T1, or Q2 upon T2 plus Q1 upon T1 is equals to 0. Summation of Q upon T is equals to 0. Now consider a reversible cycle ABA. It may be regarded as being made up of a number of Carnot cycles drawn across the diagram. Starting from A and going through all the cycles successively from A to B, it can be shown that all paths inside the closed curve ABA cancel each other, leaving only a zigzag path which is almost same as path ABA of reversible cycle. By making each Carnot cycle smaller and increasing their number, it can be made to correspond more closely to ABA. The reversible cycle can therefore be regarded as being made up of infinite number of Carnot cycles. For each of these cycles, we have summation of Q upon T is equals to 0 as proved above. Hence, for the infinite number of Carnot cycle, summation of delta Q upon T is equals to 0, where delta Q is a very small quantity of heat at temperature T during the small isothermal change of the reversible process. Further, the above term may be divided into two parts, one for path A to B, another for the back path B to A. Summation of delta Q upon T is equals to summation A to B delta Q upon T plus summation B to A delta Q upon T is equals to 0, and we can simply write Q upon T A to B is equals to minus Q upon T B to A. This implies that the total value of quantity Q upon T for the path A to B is equals to total value of the quantity Q upon T for reverse path B to A. Hence, it may be concluded that quantity Q upon T is a state function. Its value depends only upon the initial state A and the final state B and is independent of the path. Obviously, Q upon T is change in the value of a quantity or a function having some definite value at A and B depending upon the values of pressure, volume, temperature. This quantity for the function is called entropy and usually represented by the symbol S. Thus, SA is the value of entropy at A and SB is the value at B. Then we must have Q upon T is equals to SB minus SA is equals to delta S, where delta S represents the total change in the entropy in going from initial state A to final state B. Hence, entropy may be defined as a state function, the change in the value of which from initial state to final state is equals to quantity Q upon T, that is the total heat absorbed reversibly and isothermally in going from initial state to final state divided by absolute temperature at which heat is absorbed. Entropy change may be divided directly as the quantity of heat absorbed isothermally and reversibly divided by absolute temperature T at which the heat is absorbed. It is important to note that as entropy is a state function, therefore the value of entropy change during a process should not depend upon path. Whether the heat is absorbed reversibly or irreversibly during the process. However, since the derivation of above result is based on the Carnot cycle in which the heat is absorbed reversibly, therefore the expression of the entropy change is invalid only when heat is absorbed reversibly. It is better to use symbol Q reversible in place of Q. We can say delta S is equals to Q reversible upon T. Further, as entropy is a state function, a small change in its value can be represented by ds. Hence, we can write ds is equals to Q reversible upon T. Units of entropy. It is obvious that units of entropy will be calories per degree if heat is expressed in calorie. Entropy is an extensive property. It is therefore important to mention the quantity of substance involved. It is usually expressed for 1 mole of the substance. Hence, the entropy units are calories per degree per mole. If the heat is measured in joule, then the units of entropy will be joule per degree per mole. Entropy change in a reversible process. Suppose a process occurs under a complete reversible condition. The heat is absorbed by the system reversibly and heat is lost by the surrounding also reversibly. If Q reversible is heat absorbed by the system reversibly, then the heat lost by the surrounding will also be Q reversible. If the process takes place isothermally at absolute temperature T, then the entropy change of the system will be given by del S system is equals to Q reversible upon T. Entropy change of the surrounding will be given by del S surrounding is equals to minus Q reversible upon T. Hence, total entropy change of the combined system and the surrounding will be del S for the system, delta S for the system plus delta S for surrounding is equals to Q reversible upon T minus Q reversible upon T, that is equals to 0. Thus, we may conclude that in a reversible process, the net entropy change for the combined system and the surrounding is 0. There is no net change in the entropy. Entropy change in an irreversible process. If any part of a process is irreversible, the process as a whole is irreversible. Suppose that the total heat lost by surrounding is Q irreversible. This heat will be absorbed by system, but the entropy change of the system does not depend upon heat actually absorbed, but depend on the heat absorbed reversibly on quantity Q reversible. Thus, if heat is absorbed isothermally by the system at absolute temperature T, the entropy change of the system will be del S is equals to Q reversible upon T. Further, suppose that the heat lost Q irreversible by surrounding takes place infinite simultaneously slowly and isothermally at temperature T. The entropy change of the surrounding will be delta S surrounding is equals to minus Q irreversible upon T. The total entropy change of this combined system and the surrounding will be therefore delta S for system plus delta S for surrounding is equals to Q irreversible upon T minus Q irreversible upon T. Now we know that the work done in reversible process is maximum W reversible is greater than W irreversible. Further, as the internal energy U is the state function, the value of U is same whether the process is carried out by reversibly or irreversibly. Hence, delta U is equals to Q reversible minus W reversible is equals to Q irreversible minus W irreversible. Combining the results, Q reversible greater than Q irreversible. So Q is reversible upon T is greater than Q reversible upon T. Q reversible upon T minus Q irreversible upon T is greater than 0. Combining the result, delta S for system plus delta S for surrounding is greater than 0. Thus, it may be concluded that in an irreversible process, the entropy change for the combined system and the surrounding is greater than 0, and an irreversible process is accompanied by net increase of entropy. Since all the spontaneous processes are thermodynamically irreversible, it may be stated that all spontaneous processes are accompanied by net increase of entropy. This is also done this is also one of the very common statement of second law of thermodynamics. The result of the entropy change in reversible process and that in irreversible process may be combined together. Delta S for system plus delta S for surrounding is greater than or equal to 0, where the sign equal to stands for reversible and greater than stand for irreversible process. The exact calculation of total entropy change delta S total during an irreversible process when the heat flows from body B to higher temperature T2 at body A at lower temperature T1 when brought in contact with it may be carried out as follows. Suppose the heat lost by the body B is represented by Q irreversible. The flow of heat may be allowed to take place infinite simultaneously slowly so that it is absorbed by the body A reversibly and isothermally at temperature T1, which may be represented as Q reversible. The entropy change of the body B will also depend on the Q reversible. Entropy change of body B is equals to minus Q reversible upon T2. Entropy change of body is equals to Q reversible upon T1. Delta S total is equals to minus Q reversible upon T2 plus Q reversible upon T2 is equals to Q reversible 1 by T1 minus 1 by T2. As discussed above, for the irreversible process, the result given in equation may be written as delta S for system plus surrounding is equals to greater than 0. Delta of system is greater than minus delta S of surrounding. Delta S of surrounding is equals to minus Q upon T. Putting this value in equation 2 above, we can get delta S of the system is greater than Q upon T. For small changes, the above equation may be written as ds of the system is greater than minus ds surrounding, or ds of the system is greater than q upon t. Expression 4 and 6 are called Clausius inequality. These equations show irreversible process are accompanied by increase of entropy. This is further illustrated with the help of two examples of irreversible process. Spontaneous expansion. Irreversible adiabatic expansion. Suppose the system undergo irreversible adiabatic change, then dq is equals to 0. Hence, by the Clausius inequality, ds of the system is greater than 0. That is, the entropy of the system has increased further as dq is equals to 0. This means that no heat is transferred into the surrounding. Thus, ds surrounding is equals to 0. Total, hence, total entropy change ds total is equals to ds system plus ds surrounding is equals to ds system, but ds system is greater than 0, hence ds total is also greater than 0. Irreversible isothermal expansion. We know that when a perfect gas expands isothermally, its internal energy remains constant. Du is equals to 0. Hence, according to first law of thermodynamics, du is equals to dq plus dw. du plus dw is equals to 0. dq is equals to minus dw. If the gas expands freely into vacuum, no work is done. So dw is equals to 0. Substituting the equation 7 gives dq is equals to 0. Hence, by Clausius inequality, delta ds of the system is greater than 0. Further, as dq is 0. This implies that ds surrounding is equals to 0. Hence, the total entropy change in the above case ds total greater than 0. Spontaneous cooling. Suppose heat is transferred from one system at higher temperature T2 to another system at lower temperature T1. If the heat dq leaves the source and enters the sink, entropy change of the source is equals to minus dq upon T2. Entropy change of the sink is equals to dq upon T1. Total entropy change ds total is equals to dq upon T1 minus dq upon T2 is equals to dq bracket 1 upon T1 minus 1 upon T2 bracket close. As T2 is greater than T1, ds total is positive, that is cooling. Heat is transferred from hot body to cold and is accompanied by increase in entropy. Entropy change of the universe. Since all the spontaneous processes occurring in nature are thermodynamically irreversible, these are accompanied by increase of entropy. The entropy of universe is continuously increases. This result is sometimes taken as another statement of thermodynamic law. Thus, the main idea of first and second law was maybe summed up: the energy of universe is constant, whereas the entropy of universe is continuously increases and tends to maximum. The entropy change for an ideal gas with change in pressure, volume, and temperature. Consider a 1 mole of ideal gas enclosed in a cylinder fitted with frictionless piston. If an infinitesimally small amount of heat delta Q reversible is supplied to system reversibly and isothermally at a temperature T, then the entropy change accompanying the process will be given as ds is equals to del Q reversible upon T. According to first law, del S is equals to du minus del W. If the process is carried out reversibly, then the equation is del Q reversible is equals to du minus del W. Further, if the work is restricted to work of expansion, then del W is equals to P dV, where dV is the small increase in volume and P is the pressure of the system. Putting the value of del W from equation 4 in equation 3, del Q is equals to du plus P dV. Del S is equals to du plus P dV upon T. Tds is equals to du plus P dV. For 1 mole of an ideal gas, Cv is equals to du upon T. du is equals to Cv into dt. Cv is the molar heat capacity at constant volume. Pv is equals to RT. P is equals to RT upon V. P of V is the volume of the system at temperature T and P is the pressure and R is gas constant. Putting the values du and P from equation 7 and 8 in equation 6, we get TdS minus Cv dt plus RT upon V dV ds is equals to Cv dt upon T plus R dV upon V. If volume changes from V1 to V2, then temperature changes from T1 to T2, then the entropy changes accompanying the process will be given by integration S1 to S2 ds is equals to integration Cv dt upon T integration limits tends to T1 to T2 plus integration of R dV upon V integration tends to V1 to V2. Assuming the Cv remains constant at temperature range T1 to T2, equation 10 may be written as ds limits S1 to S2 Cv dt upon T integration limits T1 to T2 plus R integration of dV upon V limits V1 to V2 delta S is equals to Cv ln T2 upon T1 plus R ln V2 upon V1. This is expression for calculating the entropy change of 1 mole of an ideal gas accompanying a process when the temperature changes from T1 to T2 and the volume changes from V1 to V2. Further, for 1 mole of an ideal gas, we may write P1 V1 is equals to R T1 for initial state, P2 V2 is equals to R T2 for final state. Dividing the equation 13 by 12, we get P1 P2 V2 upon P1 V1 is equals to T2 upon T1. V2 upon V1 is equals to T2 P1 upon T1 P2. Delta S is equals to Cv ln T2 upon T1 plus R ln T2 T2 P1 upon T1 P2. We know that Cp minus Cv is equals to Nr and Cp minus when N is 1 mole, so Cp minus Cv is equals to R and Cv is equals to Cp minus R. Delta S is equals to Cp minus R ln T2 upon T1 plus R ln T1 P1 upon T1 P2. Delta S is equals to Cp ln T2 upon T1 R ln T2 upon T1 plus R ln T2 upon T1 plus R ln P1 upon P2. Delta S is equals to Cp ln T2 upon T1 plus R ln P1 upon P2. This is expression for calculation of entropy change for 1 mole of an ideal gas accompanying a process when temperature changes from T1 to T2 and pressure P1 to P2. Entropy change for an ideal gas in different process. Equation 11 gives the entropy change for 1 mole of an ideal gas when temperature and volume are variables. Similarly, equation 16 gives the entropy change for 1 mole of an ideal gas when temperature and pressure are variable. These equations are modified if conditions of constant temperature and pressure and volume are imposed. For example, if temperature is kept constant, isothermal process T1 is equals to T2, so delta S is equals to R ln V2 upon V1 is equals to R ln P1 upon P2. Alternatively, delta S is equals to Q reversible upon T. W maximum is equals to minus W max is equals to Q reversible is equals to minus nRT ln V2 upon V1 is equals to nRT ln P1 upon. If pressure is kept constant, P1 is equals to P2 and delta S is equals to Cp ln T2 upon T1. If volume is kept constant, isochoric process V1 is equals to V2 and delta S is equals to Cv ln T2 upon T1. Note carefully that all expression derived above for the calculation of entropy change involves natural logarithm. Since logarithm table commonly used are to base 10, in applying these formulae, ln x has to be first replaced by 2.303 log x, where x is a quantity like T2, T1, V2, V1. Further note that if a gas expands reversibly but adiabatically, then for such process Q reversible is equals to 0. Therefore, delta S is equals to 0. Entropy change during a physical change, phase change. A change of phase occur in one of the following cases: when solid melts, or conversely when a liquid freezes, when a liquid evaporates, or conversely when a gas condenses, when a crystalline form changes into another. When the change of a phase commences, the temperature remains constant till the change of phase is completed. The heat evolved or absorbed during the phase change thus does not change the temperature and is therefore called the latent heat. It is further termed as latent heat of melting, latent heat of vaporization, etc., depending upon the nature of process involved. In general, if delta H is latent heat and then T is temperature at which the change of phase occurs, the entropy change accompanying the phase change will be given by delta S is equals to del H upon T. The entropy change delta S is termed as entropy of melting, entropy of vaporization depending upon the nature of process, entropy of melting or fusion, delta S F, delta H of fusion upon temperature of fusion. Delta H of fusion is latent heat of fusion, melting, and TF is melting fusion temperature. Entropy of vaporization. Delta SV is equals to delta H of vaporization upon TB, boiling temperature. It may be mentioned here that process like melting and evaporation involve absorption of heat, which is taken as positive by convention of sign. Therefore, delta S for process is positive. Therefore, the process are accompanied by increase of entropy. On the other hand, reverse process like freezing and condensation involve evolution of heat, which is taken as negative. Therefore, for the process delta S is negative, and these are processes that are accompanied by decrease of entropy. Entropy change on mixing an ideal gas. Suppose at a constant temperature N1 moles of an ideal gas 1 at initial pressure P1 naught are mixed with N2 moles of another ideal gas 2 which has an initial pressure of P2 naught. Suppose after mixing their partial pressures in the mixture are P1 and P2 respectively. Now we know that at constant temperature the entropy change of an ideal gas when its pressure changes from initial pressure P initial to final pressure P final is given by delta S is equals to R ln P initial upon R P final mole inverse.